Let's go along. Oh, yeah. Okay, guys, it took me longer to get this list copied over than I wanted. I just found out that in Windows 7, there's a problem where Windows lose focus. Focus just means where, say you've got Notepad open, you're typing in that, you click over on your browser, now the browser has what's called focus. Well, my computer was losing focus every few seconds. It was practically impossible to tap. Well, what I did, can you guys do control alt delete go to task manager? Because what I did is I found that the problem was there was this program coming up called WER fault. You don't even have to go there. Oh, what you can do, what I just discovered is if you go to the Action Center, hit the flag button. I'll turn on the overhead. I'll show you what I did. How long have they been doing that?
Like
Since the beginning of the session. Oh my goodness, please tell us stuff like that so we can get them.
I don't think we realized the last class.
we thought it was one program, so it's not that problem.
When we like last class, we're like, oh, that's how you like.
Okay.
We're trying to like type in
Right, and you lose focus and there's no longer what you type. Yeah. It comes back, but really is not. Let me show you what I did. I forgot to change my resolution. Action.
The laser cutter?
And I don't know if we can let you guys control it, but we'll definitely talk.
So that is what cutter is?
And then Start Action Center. And choose Change Action Center Settings. And what I did is I just unchecked all this stuff here. Cleared all that. And I took care of my problem. Because apparently WER fault is something that's supposed to go out and check if there's a solution to some kind of a problem your computer experiences. So it just keeps interrupting the computer over and over.
Uncheck everything.
That's what I did. I just unchecked everything. It's under Change Action Center. And I didn't reboot or anything. Reboot it and send it back. See if that makes your computer stop doing it as well, okay? Let me know how that goes.
It didn't work for mine.
It did not work for yours? Okay. The other thing I did a control alt delete from Task Manager, and I noticed WER fault, and when it came up, I hit it and I shut it off. And I killed a few other things, but I'm sorry, I don't remember what all I killed. But I just did a control alt delete and sorted them by how much CPU they were using. And then, every once in a while, one would come up at the top of the list and identified it. You know, and I noticed that the window would lose focus at that time, whatever program it was I killed. So, and any program in the room goes, no, not my poor computer. Oh my God. Anyway. So that's what I did. It seemed to work. If you find something else that works, let me know, because that'll help Greg troubleshoot and figure out what's going on. But I want to talk about sampling. And to talk about sampling, let me illustrate what sampling is. I assume all of you are old enough that you've had music CDs, right? Music CD in the tray, it plays music, sounds good. And you know that it sounds better, at least to me, it sounds a lot better than a cassette tape or an old vinyl record. What was that? It's this black piece of plastic that has grooves in it and it makes sound. Anyway, if you don't know what that is, it's an old audio technology. It sounds like crap in my opinion. Okay. There's some music I still have on album. The only reason I have is because I can't find it on CD. You have to listen to it with all those dust pops. Anyway, so how does CD-ROMs work? Has anyone ever looked into how a CD-ROM works? Well, it's pretty interesting the way it works. Basically, the data is stored in a spiral pattern on the CD-ROM, a lot like an album, and depending on the format. And basically what happens is you've got a bunch of ons and offs. There's a bunch of ones and zeros that are stored that laser reads off of that disk. Okay? Now, the ones and zeros, how would they be used? Well, I've got to show you a little bit about how sound is made in the digital world, if you will, before you'll understand what's going on. So let's start off just considering what sound is. You can hear my voice because what's happening is my vocal cords and my mouth and my throat and everything together work together to cause pressure fluctuations in the air. Those pressure fluctuations move out to you, not surprisingly, at the speed of sound. Okay. Where does it come from? It comes to your ears and vibrates the eardrums on your ears, which then somehow gets converted to some type of signal your brain detects, and you've learned to understand what those signals mean. Okay? How all that works, I'm not really sure, but I do know that my voice is causing pressure variations in the air, and then I can use this set of speakers over here to also cause pressure variations in the air. If I record my voice on this computer, it'll play back and you'll hear my voice from whenever I record it. Now, how do you represent that? How do you do that? Well, basically, you need some way of representing speakers' position over time. Now, the little speakers in this or in headphones or anything that makes sound, most of them are essentially a cone, and the cone has a coil on the back of it. There's a magnet with that coil. It's basically a linear motor is all a speaker really is. And what happens is you apply voltage to this speaker in an alternating fashion to cause the speaker to move out and in. So the speaker moves in and out in order to cause pressure variations in the air, just like your voice or instrument or whatever it's recording causes. It sounds the same because it's causing the same type of pressure variation. So basically what you could do is you could look at the position of the speaker over time. So here's our little basket speaker with the magnet on the back. That's the basket. There's usually a surround here that comes down to a cone, and there's a coil on that cone that goes down, and this is what gets pushed back and forth. In case you haven't seen what a speaker looks like, by taking one apart, I'll show you what they look like. Yeah, it basically looks like this. So here's a loudspeaker, there's a voice coil in the back, there's some turns of wire that are basically big inductors. There's a magnet back here that gives you a north and a south pole on either side of the coil all the way around. And so when you apply voltage to the coil, it either pulls the speaker in, and if you reverse the voltage, it pushes the speaker out. So as long as you vary that voltage over time, the speaker will basically follow the signal. I don't know if it's a current or a voltage signal, or exactly how the electronics work, but I know it pushes and pulls the speaker, and the speaker recreates the sound. So if you were to note the rest position of the speaker here, you could plot the speaker's motion over time. You know, the motion's more complicated than this, but just for the sake of argument or illustration, I'll draw it as a sine wave. Okay? Now, a sine wave just sounds like a pure tone. We'll listen to a sine wave in just a minute. Okay? But how would you represent this signal so that you can send it to the speaker electronically, especially if you need to digitize it or make it a bunch of ones and zeros? What you would do is decide that you're going to look at this signal at various points in time. You're going to decide that there's a certain period or frequency at which you're going to look at the position of the speaker and record it. Okay? So you look at it at this point in time, it's here, you record that it's here, you record that it's here at this time, and it's here at this time, and so on and so forth. So you get a bunch of dots that when you play connect the dots, it makes that shape. Okay? Now what you have to do is decide how often you're going to take what's called a sample, and how many bits you're going to use to make up a number to represent the height of that sample. Does that make sense? Now, in days gone by, I had a Commodore 64. Now, the Commodore 64 had a SID chip in it, which had 3 voices. Those voices could not do any of this. They could not sample. They were just sawtooth waveforms and sine waves and things like that. And I was blown away the day that I got a game and I heard a very scratchy, digitized voice. Wow, this is the coolest thing ever. Okay, this is before CD-ROMs. Okay? It was 4-bit digitized sound, because it turns out that in the Commodore 64, you could control the volume of the SID chip. That was the sound chip that made. And it turned out that the Commodore 64 designer had a voltage leak in the SID chip. what would happen was that would make just a little bit of sound, and if you varied the volume along the way that you wanted the speaker to move, the speakers would actually move that way you could hear the sound. Okay, I don't know if you know anything about the Commodore 64, but it's a very popular platform for people to try to push the machine beyond its limits. Oddly enough, today there are still people programming the Commodore 64 to take it beyond what it was meant to do. They're taking it up to the point where now they can actually make 8-bit sound out of the stock Commodore 64. How they do that, I have no idea. I just know it's been done pretty much. So anyway, I'm going to play a sound for you here in a minute so you can hear 4-bit digitized sound. But let's think about it beforehand. If you only have 4 bits to represent the speaker's positions, how many different speaker positions could you represent? Almost. 16, right? Because 2 to the 4th power, right? So if you do the math, you can have the numbers 0 through 15, basically, right? So if you, that's pretty scratchy, right? It's going to sound pretty rough, but it would work. So here's what it sounds like. Now, I confess, this may be the Commodore 64 playing something with 8-bit sound instead of 4-bit. I'm guessing it's 4-bit. I haven't listened to it. Let's find out. Get ready, it's going to sound terrible.
Okay, well, this is proof that,
Fast forward what they're actually doing. There we go. You recognize it? It's really bad, right? It's really low fidelity. Of course, if you'd have hooked up the recording out from a jack, it would sound a little better. Okay, see, you probably heard this song by Bon Jovi. Let's fast forward a bit. So basically, what's going on the screen, the way it's flashing like that, I don't know if you guys could see it, but what they were doing is they simply copied the value of the sample as a color on the screen. And since there's a lot of samples going by fairly quickly, that just makes the display that is colorized, basically. That was something that was fairly popular to do back when people were trying to do all this. So that's 4-bit sound, and it sounds terrible, right? Well, what do you get if you add one more bit? What if you have 5-bit sound? Now how many speaker positions can you represent? 32. And if you have 6, you have 64, right? Well, the Amiga came along, which was Commodore's next computer, basically, and it had an 8-bit sound. Oh my goodness, you could represent the speaker's position with 8-bit sound. That's 256 different positions. Okay, that sound still sounded kind of scratchy, but it was a lot more fun to play with. And there's, oddly enough, still a scene where they make music for that platform. I don't know that you really appreciate it. I like it. If you come to my office, you'll hear me listening to weird music. It's because I like this stuff. Okay. Now then, CD-ROMs came out. And with CD-ROMs, you can have 16 bits per sample. So every single sample takes a whole long word of data, 16 bits. How many different speaker positions could you represent with 16 bits? 65536, that's the math. Okay, you can represent that many positions. 0 being one of those positions, and 0 is not right here. 0 is down here. Okay. 65535 is up here. 16-bit sound is so good that most people's ears can't detect the difference. Okay? They hear it and they're like, that sounds pretty good. I wouldn't know if that's a tape recording where it's a high-quality tape or what this is. Okay, this sounds good. Now, I'll tell you something about CD-ROMs. If you still have a CD-ROM player, and music has become more popular, instead of to fade out the song, which was popular in the 80s and the 90s, what's popular today is just end the song, right? Let's just kill it and be done. Maybe hold the chord at the end or something, and the song's done. Well, in my day, back in the 80s and the 90s, it was popular to slowly take down the faders and the song fades out and goes away. If you have a CD with the song recorded that way, what's happening is the sound, the volume, the amplitude is decreasing. So it would be something like this. Over time, the wave would get shorter and shorter. And basically, your ears interpret that as lower and lower sound pressure variation, that's lower and lower volume. The shake note is not important, it's actually a logarithmic shake. Let's not worry about all that. Well, if you think about it, when the song is fading out, what you're doing is you're using a smaller range of bits to represent the sound. So the sound actually gets scratchy. So if you have a song like that, wait until the end when it's fading out, turn it up real loud. and you'll hear that the sound, you'll still recognize the music, it'll sound more scratchy than it should. Okay? Now there's variations on that. There's DVD audio, there's super audio, where they have more bits and they try to do something intelligent so that when you've got low volume recording, it still expands the dynamic range. Let's not worry about all that. Standard CDs work this way. Okay? Now, what I'm going to do is show you what a sound looks like. The reason I'm showing you all this, I know probably none of you are going to go into the recording industry, but the principles that you're about to learn are very important for industrial systems, because in industrial systems we use PLCs. PLCs are basically computers, and the signals that you get in, even if they are continuous signals, like a continuous temperature signal, you have to digitize them. That means two things. That means you have to measure the magnitude of the signal and convert it to a number, which means you're going to have some round off, because it's not going to be a perfect measurement. And you're not going to have a continuous signal. You have to discretize the signal in time as well as in amplitude. And it's important for you to be able to decide how much resolution is important, both in time and in amplitude. Okay? The principles that we're talking about now apply equally well to any type of sensor, not just a microphone. So let's play with this microphone for a moment and see what we can get. I've got Audacity, which is a free audio editing program, and it's acting like I don't have any input devices. Let's see. There's a way to get to it, but I can't think of how to get to the sound setting. It's this way. Recording devices, there we go. And it seems to detect it.
I think you have to set it up to look at that in Audacity.
Okay.
Try to remember.
Usually, I thought there was a option up here. Let's try that. There we go. Let's try that. Test 1, 2, 3. Oh, test 1, 2, 3. Well, it usually makes a waveform. Let's try. That's all we got. I really wanted to show you guys what a sample looks like.
Oh, yeah.
Check 1, 2. It's not blocking. Let me try the back for it to see it. Usually there's ports on the front and on the back. There we go. Okay, it's mic level, not line level. Line, back panel. Okay. Now, is it relevant? Let's find out, let's monitor it. Oh, we are monitoring. Check. Okay. Okay, it doesn't like primary sound driver, let's try this. Okay. Right. Well, I don't want to waste your time trying to get this to work. I'll figure it out and get it working next time. I'll go ahead and describe what we would see. If I were able to record my voice, what would happen is you would actually see a bunch of points appear here that represent the way my mouth and my voice made the sensor in that, which is just a diaphragm, move back and forth. So what you would see is a bunch of points like this, but it would be a much more complicated signal than the simple sine wave. Okay? And so we can play with it, and what I'll do next time is put some effects on my voice. I'll let you guys say something. We'll make it echo and do some fun stuff. But I want you to see what a sampled signal looks like so that we can really zoom in, and you can see that literally the signal will be made up of a bunch of samples. There'll be a bunch of dots that are connected together, and you can see how this really works, because it's the same principle for industrial sensors. So I apologize that didn't work out. I'll figure it out and show it to you next time. Now, let's continue with the CD-ROM. Have you ever heard the specifications of the CD-ROM that it's 16-bit, 44.2 kilohertz? You ever wonder what that means? Well, the 16-bit hopefully makes sense now because that's telling you that you're representing the speaker's position with 65535 different steps. Okay, there's that many different positions. Now, some artists, okay, you're going to find out on the real beat. Some artists have really good recording where they are very careful about the recording. I confess, I'm a Weird Al Yankovic fan. Okay, that's just, I admit it. I only saw him last time he was in town. It was a pretty good show. Okay, but if you notice, if you ever, I don't like using my CDs, I like to put them away, so I bought one of these CDs and I ripped it, which means I copied the information off it into free, so I can play it in my car, right? So, or on my player device. But anyway, what was interesting about it, in the process of ripping, I noticed that all of his songs go up to exactly 99% of full range. These are all normalized so that the sound quality is as high as possible. So either he or someone is a pretty good recording engineer that works for him. Okay? But anyway, you want to use as many of these steps as you can. You want to use the maximum bit range so that you can get the maximum dynamic range and represent the music as accurately as possible. In Pro Audio, the recording devices there go up to 20 and 24 bits. So you have even more bits to represent the signal and make it higher quality. Anyway, back to the other specification, 44.2 kilohertz. Does anyone know what that means? Everybody?
Sample rate.
It's a sample rate, that's right. And you've got two channels. CD-ROMs are, or not CD-ROM, but CD audio is two-channel sound. You've got a left and a right speaker. Now those two speakers move a little bit differently. They don't move exactly the same if the recording is actually stereo. Okay? So you have to record two separate signals. And so what they do in the other channels, they do the same thing, but the 44.2 kilohertz is kind of a misnomer because we've already said the 16-bit how many steps we have, but they haven't told us how it's discretized in time. It turns out what they do is they sample, or they measure the speaker's position 22,100 times every second. That's a lot of measurement. Okay? But that's literally what the sound card in the back of your computer or the recording device in a studio would do. It would measure that sound that many times at least. Okay? Now, in Pro Audio, they typically record at even higher rates, although it's unnecessary, but it's good for mixing down and for modifying the waveform in post-production. Anyway, all that aside, your CD audio is putting out 22,100 samples every second for each channel. So the sum of 22,100 for both channels comes out to 44,200. That's where it comes from. If there was a sound that was going back and forth at 44,200 times per second, no human being's ears on the earth could hear it. Our hearing simply doesn't go up to that range. When you're young, your hearing goes up maybe to 20,000 hertz or 20,000 cycles per second. So you could hear a waveform that's literally going back and forth that many times per second. As old as I am, there's no way my hearing goes up to that. I'm probably lucky if I can reach 10,000 cycles per second. It's just, as you age, your hearing range falls off. The low end falls off, the high end falls off. That's just part of it. That just means you have to crank the music up loud. Right? Okay, so anyway, does that make sense? So the key takeaways here is that any signal, any continuous signal, like a temperature sensor signal or a pressure signal, or even a position signal, you have to decide how often you want to sample it, okay, in time, so how you're going to discretize it in time, and how many steps you need to accurately represent and have useful information. So let's talk about something like measuring, flow rate. So what we're going to try and do is measure flow rate over time. Now, let's say we're talking about flow rate at the Hoover Dam. We need to know how much water is going over the edge and we're measuring it, okay? How often do you think it would be necessary to measure the flow rate? Do you think would you need to measure that 22,000 times every second? Probably not. That's probably excessive. Would once every second be adequate? It depends on what kind of control you're trying to do, but once a second is probably reasonable. I mean, once every minute may be reasonable. Who knows? Okay? And so you might decide that you don't need to take a sample or a measurement from that sensor every 20 seconds, maybe it's every second. Okay, so 1, 2, 3, 4, 5 seconds. And then you might have to decide, well, how accurately do I need to know? In other words, what's the resolution with which I'm going to measure the flow rate? Let's say the flow rate has a maximum, and I'm making this up. Anyone have a ballpark idea of the GPM up or down? No idea? Okay, let's make it up. Let's say it's 100,000. 100,000 GPM. I don't know if that's reasonable, small, I don't know. So we can go anywhere from 0 GPM, because I don't think we can convince the water to jump back in the middle of the dam, right? So it's anywhere from 0 GPM up to about 100,000 GPM. Now, do we need to know this flow rate within 1 gallon per minute? Probably. Maybe thousands of gallons per minute. Does that seem reasonable? Okay, so let's say we want to have a resolution of thousands. So basically, how many tick marks would we need here? We need 100. Or 101, so we can do it with 0. But let's just say we need 100 to make it simple. Okay? So we want a resolution of 100. How many bits would we need in order to represent 100 different levels of something? Well, let's see. With 1 bit, you can represent 2 levels. 4. And let's see, then there's 8, 16, 32, 64, 128. We need 7-bit resolution. Can you find a 7-bit microprocessor, ECETs? Right. You're going to get an 8-bit microprocessor. So why don't we just bump it up to 8 bits? And with 8 bits, how many levels would we have? 256. So we'd have 256 different flow rates that we could represent. If the flow rate was somewhere between, so that we're waiting until we go from a flow rate of 250 to 251, then we're between. Maybe we round it off. But let's figure out what the resolution is here. This is the last thing I want to talk about, really, is resolution. Well, there's one more topic that's simple. Okay, in resolution, what we're trying to do is figure out how much the variable has to change by a single count change or a least significant bit change. What do I mean by that? Well, if we've got 8 bits, then when we go from 250 to 251, all we're doing is flipping this bit. And this is the so-called least significant bit. This is the most significant bit. And that makes sense because this is the ones placed 2, 4, 8, 16, 32, 64, 128. Okay, so this is the most important one. If we flip this one, it means we've got to change 128. If we flip this one, it means we've got to change 1. Okay? So the question is, if the least significant bit